For the rest of today, well, for most of today, we want to step back now from chemical reactions and talk about the way that the molecules themselves are put together. This is not something which is explicitly covered in Chem 191, but it is something you kind of have to have a bit of a feel for. It's kind of assumed knowledge for Chem 191. So, how are molecules held together? The molecules which we've been talking about so far are composed of atoms which are held together by something called chemical bonds, which as yet we haven't really discussed in any detail. And so what we want to do today is look at what these chemical bonds are, look at the different types of bonds, and obviously the bonding is important for trying to understand the chemical properties of the compound. Different sorts of bonds endow a molecule with different sorts of chemical reactivity. And there's 5 points if anyone can tell me what that molecule there is. Even though I'm guessing 2/3 of you consumed some of this morning. It is caffeine. Okay. So it turns out that there's kind of two different main types of chemical bonding. In reality, those are extremes in a continuum of chemical bonding, but for the moment, we'll consider them as being kind of separate, and then at the end, I think we'll talk a little bit about how there's actually a continuum. So, the first type we want to look at is something called ionic bonds. And ionic bonds are kind of obvious in some ways because, from the name, because ionic bonds are what you get between ions. So it's the type of bonding that you find in ionic solids, like sodium chloride. Yeah? And so ionic solids are the ones that are composed of cations and anions. And what you find is in an ionic solid, the ionic bond is just due to the so-called electrostatic attraction between the positive charge on the cation and the negative charge on the anion. And there's a couple of little blobs there representing a sodium cation and a chloride anion. The chloride one's bigger, because it is, but this is something we're going to get into right towards the end of the course, so for the moment it's not a big deal. Okay, so an ionic bond is just there due to the electrostatic attraction between a positive charge on a cation and the negative charge on an anion. In an ionic compound, in the solid state, so if you like little crystals of salt, then the cations and the anions are arranged in a very regimented way within the solid so as to maximize how many of these attractive interactions you have. Right? So oftentimes it's something like this, where you have your cations and your anions alternating in this very regular, this is obviously drawn in 2 dimensions, but in reality it's in 3 dimensions. So that you get lots and lots of these positive, negative, attractive interactions, and as much as you can, you minimize the positive, positive, and the negative, negative repulsions. And so if you're a piece of sodium chloride, then obviously in sodium chloride you have the same number of cations and anions, and so an arrangement like this kind of works because in that arrangement you need to have the same numbers of each type. If you're a magnesium chloride, where you have twice as many chlorides as you have magnesium ions, then the structure is going to be subtly different, right? So as to maximize the number of cation-anion interactions. But they're all kind of similar, right? And we don't have to worry about the more complicated ones. So that's kind of the way that sodium chloride would be. The strength of the ionic bond will depend on the size of the charges and on the relative sizes of the cation and the anion, at least in the solid state. The relative sizes of the cation and the anion, right? So it kind of makes sense for the charges. If you have a magnesium 2+ ion, then its interaction with a chloride will be stronger than if you have a sodium 1+ cation with a chloride, yeah? Because the charges are different, you've got a 2+ charge rather than a 1+, so it's going to attract the negative charge more strongly. So the charges matter. The relative sizes, it's a little bit more subtle, but what you would imagine is that if you have, because different cations are different sizes, yeah, and again we're going to talk about this later, but as you go down the periodic table from say lithium to sodium to potassium to rubidium, the atoms are getting bigger and bigger and bigger, so the cations are getting bigger and bigger and bigger. There's more electrons, more shells. Yeah? And so if you were to compare, say, this is the bottom here, so let's imagine, as opposed to the previous picture where it was sodium and chloride, let's imagine this is rubidium and chloride, so now rubidium's much bigger, then even though it's still 1 plus and 1 minus, now you can see they don't pack together so well, because they're much different sizes compared to each other. And so now you have significant plus-plus repulsions. Actually, I'm doing this all wrong, aren't I? The bigger ones are going to be the anions. Anyway, it doesn't matter. The green balls are much more in contact with each other here, and so that's going to be a repulsive force, right? Because whatever the green ones are, they're going to have the same charge. And so a solid like that, you would expect to be weaker, and so more readily broken up than one where the cation and the anion were much the same size. Does that sort of make sense? Assuming you could get solid HCl, yes. I don't think you can actually, but yeah, I see what you're saying. And so one place where you do see this manifested is in things like solubility. Right? So sodium chloride is quite soluble in water, but you might imagine another solid where where the packing is much better and the ionic bonds are much stronger, that compound would be less soluble in water. Any sort of deeper description about ionic solids rapidly turns into using math to describe how big the interactions between the positive and negative charges are, and it gets nasty. So that's about as far as we ever go now. Okay, so this makes sense? We're happy?
Does it work in the opposite as well? Like if the anion is much smaller than the cation, is it a much stronger bond?
If this difference in sizes between the two ions is very big, regardless of which way around, that will weaken the bond. Well, it'll weaken the bond in the solid because it will increase these repulsive interactions between the anions or the cations, whichever they are. If you dissolve it up and so it's in water, then it's different. But then it's not really an ionic bond anymore. We'll get to that. Yeah. Okay. So ionic bonds are kind of interesting so long as you're talking about an ionic solid. But the vast majority of the interesting molecules in the world aren't ionic solids. And so in those cases, we have a different sort of bonding, which is called covalent bonding. And covalent bonds are quite different because unlike in an ionic bond where the attractive interaction between the two ions comes from the electrostatic attraction between the charges, in a covalent bond, we're not necessarily talking about ions at all. We're talking about atoms that don't have charges, and so instead, the thing which holds a covalent bond, holds atoms together in a covalent bond, is the sharing of a pair of electrons between the two atoms. And so what we're going to do is we're going to start by considering the simplest possible molecule, which is the simplest possible covalent bond, which is H2. If I asked you to write the electron configuration of a hydrogen atom, you'd probably be quite pleased because it's about the easiest one going. It's 1s1. Okay, a hydrogen atom has one electron only. It'll be in that 1s orbital, that lowest energy orbital. And so that means that if you want to make bonds using hydrogen atoms, the only electron the hydrogen can use is that one electron that it's got. Right? So each hydrogen atom has one electron which it can use to form a covalent bond by sharing it with something else. Yeah? So if we have two hydrogen atoms, they can each share their electron with the other hydrogen atom, and so that can form what we call a single covalent bond. Remember, a covalent bond is a pair of electrons being shared between two atoms. So in this case, we can make a pair because we've got two electrons. One comes from one hydrogen atom, the other one comes from the other hydrogen atom. And so we can kind of draw little pictures to describe this. Here's a hydrogen with a dot, and another hydrogen with a dot. So the dots are the electrons. And what we can do is if we bring those two hydrogen atoms together, then we can draw a picture like this, where now those two electrons are being shared between the two hydrogen atoms. And that sharing of that pair of electrons between them enables the two hydrogen atoms to stick together. And so we can draw that like that, where that line indicates a covalent bond. Okay. So, the little diagram that we just drew, this little one here, where we have the atoms and then we have these little dots indicating the electrons that the atoms have that they can use to make bonds. This is an example of something called a Lewis dot diagram, which was named after Gilbert Lewis, this dude, who invented them way back in like the 1910s. I should point out that he probably wasn't that old when he developed them, right? This is a thing. There's a guy called Harry Kroto. Have you heard of Kroto? You heard of buckyballs? Some people? Kroto was one of the guys who discovered buckyballs and won the Nobel Prize for Chemistry in the year 2000, and he was out here a few years back and gave this very random lecture, it has to be said. But one of the points he made in it, which I thought was very good, is that when you think of Einstein, what is the immediate picture you think of when you think of Einstein? But if you had to imagine him, what is the picture you have? Crazy old man with crazy hair, yeah? When he came up with E equals mc squared, he was 23, right? He wasn't a crazy old man with crazy hair, he was a young guy. Same with Rutherford. You imagine Rutherford like on your money, if you're that rich, as an old man. But when he developed the picture of the atom, he was a young guy. He was in his 20s, yeah? All of these, we have these images of scientists being old men. Even Mary Curie, oftentimes you see pictures of her being an old woman. She wasn't that old because she died, but they were actually young people who did this. You know, younger than me, heaven help us. De Broglie, who we're not going to talk about, but who came up with this idea that waves and particles are the same thing, so all matter is actually a wave as well. He did that for his PhD, for crying out loud. Right? So he's probably like 21 when he came up with that. Young people do science, not this. This was an old man when he was rich and old. Right, anyway. Remember we talked about orbitals Monday. In terms of the orbitals, we can imagine the 1s orbitals on each of the hydrogen atoms merging into one new orbital which contains both of the electrons. Right? So this is a little step towards a slightly different way of thinking about how bonding works. This isn't strictly Lewis dot diagrams now, but this is just giving you a wee taster of the stuff that you will do if you do second semester chemistry with us this year, not Halsey. So we can draw big circles like this indicating our 1s orbitals, and we put the wee dot in there indicating there's an electron in that 1s orbital, and when we bring these two hydrogens together to make this new bond, we make a new sort of an orbital for that pair of electrons to live in. And so we tend to call the 1s orbitals that we start with atomic orbitals, because they're orbitals on atoms, and the one at the bottom we call a molecular orbital, because it's an orbital that you find in a molecule. Right? There's lots more about so-called molecular orbital theory, which, like I say, if you do chemistry in second semester, we spend lots of time talking about it. But I'm not going to do too much now, but that just gives you an idea of how the orbitals work. But what we're mostly going to focus on now is just the electrons, right? Okay, so let's consider now a slightly more complicated molecule. Let's look at methane. So methane has the formula CH4. It's a carbon with 4 hydrogens attached to it. Yeah? And so again, if we look at our electron configurations, hydrogen is 1s1, so it has 1 electron. Carbon has the electron configuration 1s2, 2s2, 2p2. So in theory, it's got 6 electrons that it could use to be sharing with other things and making bonds. Yeah? But while the carbon has got a total of 6 electrons, only 4 of these are in the outermost orbitals. Remember the other day we talked about onions, yeah? and how the electrons are in shells like the layers of an onion, and when we try and stick two onions together, we have to stick them together using the outermost shells. So it's the same deal here. If we want to make covalent bonds between the carbon and the hydrogens, we can only use the outermost electrons on the carbon, not the inner ones, because they're in the inside and you can't get at them, right? So we're only going to care about the 2s and the 2p electrons on our carbon. So that means we've only got 4 to play with. And we give these a name because these 4 electrons are in the outermost orbitals. They are the ones most easily used to interact with another atom, and so they're given a name. They're called the valence electrons. Valence is a very old chemistry word, but it just means the outermost electrons, the ones that we can use to make bonds with other things.